In this video, you will use the pipe segment in aspen hysys to create simple hydraulic piping model. You will also learn how to use the flow assurance options in the pipe segment to study flow viability and operability for a variety of process conditions. In this example, a gas liquid hydrocarbon gathering system located on a varied terrain is simulated using the steady-state capabilities of aspen hysys. This figure shows the physical configuration of this system superimposed on a topographical map. The system consists of 4 wells distributed over an area of approximately 2 square kilometers, connected to a gas plant by a network of pipelines. The gas in this case is varied. Both sour and sweet gases are being combined in the pipeline, as well as a gas condensate mixture. One well even includes some produced water. A variety of fixtures and piping manifolds combine all of the incoming streams from the outlying wells into one common header. Flow lines extending from the central site to each of the individual wells are modeled in aspen hysys using the pipe segment operation. Since the plant is located in an area with mixed terrain, the elevation changes must be accounted for in the pipe segment operations. An insulated Schedule 14 steel piping is used throughout, and all branches are buried at a depth of approximately 1 meter. Mixer operations are used to model mixing points where flows from remote wells are combined in common lines. This video includes the following tasks. Task 1. Add the first branch. Task 2. Complete the piping network. Task 3. Perform flow assurance studies. Task 1. Add the first branch. The fluid package details and material stream conditions for the 4 gas wells have already been defined in the attached hysys simulation file with this video. So much of the initial information has already been supplied for your pipeline model. The component list is comprised of the standard assay management components, as the gas well for material stream is defined using a petroleum assay. The other inlet streams is characterized with defined mole fraction composition. Bing-Robinson equations of state is defined as the property package. Ensure that the 4 feed streams have the following specifications. In this simulation, several individual pipe segment unit operation will be used to represent the gathering system pipeline. In addition, each pipe segment operation may contain multiple segments to represent the various elevation changes across the pipeline environment. Add the pipe segment. Set the inlet stream to gas well 1. Name the outlet stream and name the energy stream. On the parameters page, you can select the correlations that will be used to determine pressure drop for the multi-phase flow calculations. If desired, separate correlations can be used for horizontal, incline, and vertical flow. Unless otherwise specified, the default method developed by Bex Brels 1979 is used. However, your piping network will make use of the more recently developed method, the Tulsa Unified Model. Please note that for single-phase streams, the Darcy equation is used for pressure drop calculations. A user-defined pressure drop for the pipeline segment can be supplied. In this example, it will be left empty as it will be calculated by the selected pressure drop correlation. On the rating sizing page, you can construct the full elevation profile for the pipe segment operation. Each pipe section and fitting is considered to be a segment. In addition to the elevation, you must also specify the pipe schedule, diameter, pipe material, and the number of calculation increments in order to fully define the pipe section. Add the first segment to the pipe unit operation by clicking the bit segment button. Set the length to 152 meters and the elevation change to 6 meters. Please note that horizontal pipe sections have an elevation change of 0. A positive elevation change indicates that the outlet is higher than the inlet, upward flow, while a negative elevation change indicates that the outlet is lower than the inlet, downward flow. Click the View segment button. Select pipe schedule 40. Aspen hysys pipe segment contains a database for several pipe schedules. From the nominal diameter drop-down menu, select 80 millimeters. The outer and the inner diameters will be calculated based on the nominal size. Keep the default pipe material and roughness. 2 more segments are needed to complete the branch. Click the Append segment button twice and enter the following data. Once all 3 segments have been added and defined, the pipe segment will not yet be able to solve because no heat transfer information has been specified yet for the pipe. Activate the estimate HTC and complete the inputs as shown in the screen. Now the branch 1 is fully defined. Task 2. Completing the pipe network. The remaining pipe segments will now be added to the flow sheet to complete the pipe network. Add 2 pipe segments to the flow sheet and use the following specification. The first one is called branch 2 and the second one is called branch 3. On the sizing page of branch 3, we change the number calculation increments from the default of 5 to 10 for each segment. This will make it easier to calculate the 3-phase flashes along the length of the line that are required by the 3-phase Tulsa unified model. Please note that the flow from gas well 3 will be a 3-phase fluid, as there is some water present along with the hydrocarbon, gas, and liquid. To properly accommodate this 3-phase flow, we use the 3-phase Tulsa unified model. For other lines that don't have any water, the 2-phase version of the model will be sufficient. You can see that branch 3 is not yet able to calculate at this point. Considering the known parameters, the piping geometry and fluid flow rate are known. However, both the inlet and outlet pressures are unknown. One of these pressures need to be fixed before the pipe segment will calculate. Add a mixer unit operation. Change its name to Junction 1. Add B1 out and B2 out to the inlet streams. Name the outlet stream G1 out. Keep the pressure assignment parameter to its default value. At the pipe segment downstream of junction 1 with the specifications provided in the shown table. Add a second mixer to your flow sheet. Name it junction 2. Add B3 out and B4 out to the L streams. Name the outlet stream J2 out. You can see that junction 2 mixer hasn't yet solved it, as the pressure assignment is set to its default value, set outlet to the lowest inlet. For this option to work, the inlet pressure of the inlet streams to the mixture must be all defined. In our case, the best option for automatic pressure assignment is equalized all. Now add a pipe segment downstream junction 2. Enter the following specifications. Please note that this branch will have water flow, so it's important to set the model to the Tulsa Unified Model 3 phase. After that, tie in the last well, gas well 4, with the pipe segment using the following data. First, there is no water, so the Tulsa Unified Model 2 phase is enough. Add one final mixer. Rename it to junction 3. Add B5 out and B6 out to the L streams. Name the outlet stream G3 out. Set the automatic pressure assignment to equalize all. Add one final pipe segments downstream junction 3 mixer. Please note that here we commingle a branch with water and a branch without water. So the commingled branch will have water. For that, we will use the Tulsa Unified Model 3 phase. The Profiles page under the Performance tab provides a summary table for all the segments that comprise a given pipe. The distance, elevation, and number of increments are displayed for each segment. By clicking the View Profile button, you can access the pipe profile view, which provides detailed information for each increment within the pipe segment. The table includes several variables to be monitored. Looking, for example, at the vapor velocity, you can see that the velocity increases as the fluid passes through the pipe. This is because the volumetric flow rate of the vapor is increasing due to the flashing as well as to expansion as the static pressure decreases. Task 3. Perform flow assurance studies. The hysys pipe segment features 5 powerful flow assurance calculation capabilities. These calculations check the physical structures of the pipe itself versus the predicted wear caused by the type of fluid being conveyed. This allows the process simulator to quickly and easily judge the viability of a pipeline over time based on whatever fluid is being modeled. The particular flow assurance calculations that can be performed are as follows: hydrate formation calculation, rate of corrosion due CO2, erosional velocity, slug flow analysis, and finally, wax deposition. You will investigate a few of these flow assurance concerns on the branch 7 pipeline. Open branch 7 and select the flow assurance tab. Begin by checking the original velocity. Keep all the default settings. Check on the do original curve. You can see that the fluid velocity is exceeding the original velocity. In order to avoid exceeding the original velocity, you need to increase the diameter of the pipeline. Let's change the nominal size of the pipeline to 200 millimeters and see the effect of this on the original velocity. Now the fluid velocity is below the original velocity. Let's set back the size of the pipe to its original size. Now we will perform another flow assurance analysis. Slug analysis. Keep all the default settings and check on those slug calculations box. From the status column, you can see that the fluid regime is a slug flow, and the slug frequency is outside model limits for slug flow. You can also check the slug length along the pipes at the pipe lengths, as well as the slug velocity. Now let's do one final exercise. Assuming that field measurements suggest that the gas is being delivered to the gas plant at a temperature of 38 degrees centigrade and the pressure of 3103 kilopascal. We want to check if we can make the flow sheet calculate in such a way that the hysys back calculates the gas well stream pressures after specifying the new field measurements. The stream B7 out represents the feed to the gas plant. As you can see, it's already calculated. You cannot manually enter the temperature or the pressure. So since pressure is being fixed at the outlet of the network, all inlet pressures should be removed. Then you should be able to enter the given temperature and the pressure at B7 out stream. Delete the inlet pressure of gas well 1 and 2. Now you can enter the B7 pressure and temperature. You can see that the network hasn't solved completely. Change the automatic pressure assignment of junction 1 mixer to equalize all option. As you can see, changing the pressure assignment in junction 1 resulted in enthalpies around the junction 1 being overspecified. This can be eliminated by deleting the temperature of either gas well 1 or gas well 2. This concludes Build a Gas Gathering System video. Thank you for watching.